There we go. We're in business. Okay. So some of these relationship problems might give you a little stress tonight. So let's go over a couple of them. We'll go over 1 and 9 from this W5.13. So question 1, a rocket travels from 4 Earth radii away from the center of Earth to 2 Earth radii from the center of Earth. What happens to the rocket's weight? Now, you could attempt to solve this problem with Big Ugly. The trouble is you don't know the rocket's mass. So if you go to run the numbers on this one, adios. If you go to run the numbers on this one, you're going to run into a little bit of a roadblock. What's actually better for you to notice here is that something has changed. The R has changed. Now, a visual for the rest of this course, when you look at a problem and you feel like, I'm not sure what to do, introduce a visual. So here's the visual. Here's the Earth. The rocket is 4 Earth radii away from the center. So here's the center. 1 radius away from the center is, of course, on the Earth's surface. A second gives you 1 radius above the surface. A third, and then a fourth. This location here, you can say, is 4 times the radius of Earth. That's actually what R equals. R equals 4 Earth radii. To begin with. So far, so good? If anybody has trouble in the room, holler out, because the people at home will have the same trouble. Now, the rocket is going to move. It's going to switch to 2 Earth radii away from the center. So whereas it was here, 2 Earth radii from the center will bring you, here's 1, here's 2. This distance right here, its R is now twice the radius of Earth. You can put numbers in there if you want.
Ms. Calise, please call the main office. Ms. Calise, please call the main office.
We're not going to put numbers in there. It's better for you to recognize that this is what happens to the rocket's weight. They're asking about what happens to FG. Now notice here the phrasing. What happens to? Are they asking you what is the weight?
No.
Right, doubled, halved, tripled, all that junk. And what I used for that were arrows instead of equals, just to remind us that we're not going to get what weight is equal to. Really what this is saying is weight becomes what? That's why I'm going to put an arrow there rather than an equals. Now, we need an equation to do this. There's only one equation that's going to connect FG with R. That equation, of course, is Big Ugly. Gm1m2 over r squared. That's the equation. That is an equation. That's why it carries an equal sign. But now we're going to substitute in multiples. How has this changed? So FG now becomes. Did Big G change?
No.
In fact, Big G never changes. Notice here, we're not putting an equals, we're putting an arrow. Because it's just becoming. We're looking at the multiples. Big G did not change, call it a 1. Did the mass of the rocket change? No, there's no comment about its mass. Did the mass of the Earth change?
No.
So that also gets a 1. All of this over. Did the R change?
Yeah, you got it squared.
How so? Correct. It went from 4 radii to 2 radii. The R rather, is now half of what it was. So when you plug in over here, the R is now half of what it was. And of course, the math maintains. There's a square over there, there's a square over here. And so this finally becomes, you're not sure, pop it in the calculator. 1 over 0.5 squared. And by the way, should it get greater or should it become lesser? The rocket is moving toward Earth. When you move closer to the object, should it become heavier or lighter? Should gravity pull harder or weaker?
Oh, wait, no. More.
Yes, it should become more. And if you put 1 over 0.5 squared, what do you get? 4. That's 1 over 0.25, which is 1 over 1/4. Keep change, flip, 4. Quadrupled. You see that?
Yes,
This,
sir.
by the way, is probably the most difficult style of relationship problem that you'll get in this course, is the moving problems with gravity. So that's as hard as it gets. So that's question 1. Then question 5 is also homework, but you guys should be able to mess with this guy a little bit. Think about this one. Then the next one that's on the homework is question 9. Let's talk about question 9. Cut that lovey-dovey nonsense. Question 9. Now they provided us a given. Get ready. Hands on the pen. Let's go. Your fancy European pen.
Yeah, I know you like them.
Well, can't deny it. They told you the 500 Newton astronaut. 500. What is that, by the way? I'm giving it away over
That's
here.
force.
Which force? If I describe you as a 500 Newton person, what about you am I discussing?
Gravity.
Your weight.
Yeah. Oh, that's weight.
That's weight. If I call you a 500, it's newtons. Newton is always a force. Straight away, you see the unit Newton, you know it's F. It has to be F. It's Newton.
So if you call something Newton, like
yes, if I name it, a 500 Newton desk is its weight.
Okay.
An 800 Newton person is their weight. So this is FG. What with a fig Newton?
No, big Newton, because you said a Newton is weight, and you said that it's F.
Holy cow, you're a genius.
I know.
He might be right.
I
always want. Well, I mean, fig Newtons are made. I mean, they're made with figs. But this is a fantastic connection. Look, fig, Newton, FG, fig. New things are discovered every day. Those of you who are watching this at home, you better give a thumbs up just for that. Don't put a thumbs down, even though it doesn't show anymore anyway. All right. So I kind of missed the dislike part, but
you made some weird comments there.
anyway, FG is 500 newtons. Cool. Now they tell us the astronaut travels. This is a good question. This is a tough question. Pay attention. The astronaut travels from the surface of some planet to a position that's 5 times as far from the center. Okay. Notice something's changing. Could be a relationship problem. What is the astronaut's weight at the new location? Ooh, what's that?
How is that a relationship problem?
Well, you'll see. They gave us an FG, right? You're right.
Oh,
They said, what is the weight? So you're going to have to come over here. You're going to have to write FG as question mark. Now, if you see this, I got news for you. The answer is probably not 500. Right? Let me give you a separate example. If instead we had like the mass is 10 kilograms, and on the Earth, like mass on Earth, and then we said mass on Moon, what is it? If it's mass, yeah, it's going to be 10. If it's mass, it's going to be 10 because mass doesn't change. But this question is not about mass. This question is about weight, and weight does change with location. Did you make a drawing?
No.
Well, here's planet Y. That's not a bad circle.
That's a pretty bad circle.
Listen, with your wobbly wrists over there.
Full square.
I know. But it's not terrible.
It's good.
Anyway, there's planet Y. Now let's start this out. They travel from the surface of planet Y. Now this one's a little tricky right here. Here's the surface of planet Y. Yes? What is the R at the surface of planet Y? Oh, there is none, huh? But there is. Because R is defined as distance between centers. So what is the R on the surface of planet Y? Hold on, you're going too fast. We're not at the 5 yet. We're starting out at the surface. What is the R at the surface? You said it twice. Don't say it anymore. You're correct.
Oh, okay.
R is the distance between centers. What is the R when you are on the surface? Yes. It's one. No, it's one. It's one radius.
It wasn't even the value of it.
Well, we don't know that because nobody told you planet Y's radius. But here for this one, R is one radius of planet Y.
Oh, okay.
Do you understand?
Yes, sir.
Now, we move to 5 times as far from the center. So here's the center, right? Let's move. 1, 2, 3, 4, 5, What's our new r here?
5R.
5 of the radius of planet Y. Now, do you see why this is a relationship problem?
Now
Yeah, that's the thing. Because I didn't give you enough givens to do it otherwise. You didn't know what the radius. I didn't tell you the radius is, whatever it is, 6 million meters. I didn't tell you. So now, here's how you. This is the 2-step. This, by the way, put a little asterisk. That's the hardest relationship problem you can get, right here. In terms of physics, relationship problems is the analog of being married. Old people joke. Anyway, there you go, somebody. So let's go over here. Fg, we know, is G m1 m2 over r squared. However, all we know is that it has changed by a multiple, which means we can't plug in the equality. But we can plug in the arrow. Fg becomes. What happens to G?
1.
You guys think. Don't lag with the pen here. Think. What happens to the mass of the astronaut? Hasn't changed. What happens to the mass of planet Y? Hasn't changed. What happens to the distance?
5.
Notice it was at 1, now it's at 5. It multiples. It's never additives. It's always multiples. It is 5 times as far. 5 squared, which becomes 111 over 5 squared.
125.
Yes, it becomes 1/25. Now, the reason that this is the hardest of the relationship problems is because we're not done. We're not done. We haven't answered. That's why I put a question mark over here. We have not yet answered the question. What is the new weight? Don't call it out. What is the new weight? It's actually not a hard thing to calculate. Calculate it. Fig Newton's not the answer. You can't say that forever. You agree? That's it. If it started at 500 and it is now 1/25 of what it was, then 500, the original force, times it becomes 1/25 of what it was, which is just 500 over 25, which is just 20 newtons.
How'd you break your board? What's up with your
I
board?
didn't. It's a little wobbly now. It's not broken.
How'd you do that?
Don't worry about that.
Did you punch it?
No. Be careful. You were a suspect in the first board issue.
I found the problem.
You were falsely accused, right?
I was.
Don't falsely accuse. All right, and then what I tell you to do, I told you to do 14 on this page, which is not too hard. All right, good. That's enough for you to be able to handle this here, John.